today we're going to be talking about atoms, compounds, and elements. And atoms are all around us. Everything that we know of is made up of atoms, and then depending on how you put those atoms together, we can build a lot of different things. We can build, carbon compounds, which help build the structures necessary for life. We can build, nutrients and materials. We can build rock. We can build all types of things, and then the atoms are going to build everything, right? Because everything that we know of is made of atoms. So today we're going to be looking inside that atom, looking at its component parts, and then looking at what we can start to make when we put some of those atoms together, and depending on how we combine them and how we allow them or how they combine themselves. So just to start, the atom is the smallest, most basic structure of matter. Again, everything that is matter is made up of atoms. So, and the atom itself is made up of protons, neutrons, and electrons. And the protons and neutrons we're going to find in the nucleus of an atom. So inside the nucleus of an atom, we're going to find protons and neutrons. These kind of all look the same, but there's going to be a mass there at the center of the atom, and that is our nucleus. Okay, and the protons are going to be there. The protons have a positive charge. Okay, and there are also structures there called neutrons, and neutrons have no charge. They are neutral. Okay, so if we just had this, then all atoms would be positively charged, and they are not. Swirling around the nucleus, we have electrons. And electrons have the negative charge. So that's what allows atoms to have a net neutral charge, is because you have a positively charged nucleus, and then you have negatively charged electrons moving around that nucleus. So electrons are the key to allowing atoms to bond with one another. So if we're going to make, a compound, or we're going to create some type of molecule, it's the electrons that are interacting with one another, not the nucleus of the atom. The nucleus of the atom is very, very tightly held together. There is a nuclear force that holds that nucleus together, and it's a very, very strong force. So there's not a lot that breaks that nucleus apart. Because the force there is just so strong that it ensures that nucleus stays intact. Okay, so the electrons, they're very, very small. They're moving around very, very quickly. The little drawing that I did there for you, that's more of an older version of what we think atoms look like. That's the Bohr model, where the electron is just kind of swirling around the nucleus. What we have now is more of an electron cloud model, where the electrons can be anywhere at any given time because they're just moving so fast, right? They're just somewhere outside of, rotating around the nucleus. And again, they are what's interacting with other atoms. And really, that's what's interacting with all things. The electrons in the atoms that make up my hand are interacting with this table, right? And those electrons are coming into contact with one another. So each atom should have a equal number of protons and electrons, and that's what gives the atom its overall equal charge, right? So we don't want to have a negatively charged or positively charged. So if it has 12 protons, it's going to have 12 electrons, and they cancel each other out, and you wind up with a neutral charge. So when you have a substance that is all made up of one type of atom, that is called an element. So when we talk about something being pure gold, that means that sample that we are looking at or that we are holding is nothing but gold atoms. It's not mixed with anything else. Nothing else has been, put in there. It is just pure gold atoms, gold all the way through. And that's how it is with any material that's pure. It's going to be an element. And some elements are perfectly fine on their own. Like an element like gold, it's going to stay gold. It's not going to react with anything else. Other substances, however, if you're going to find them as an element by themselves, you're probably going to have to do something to ensure that they stay just that element. For example, like sodium is a highly reactive metal. If you want sodium and you want to see it in its elemental form, you have to keep it in a metal container, because if you don't, it's going to react with water in the air, or it's going to react with oxygen. If it reacts with water, it's very violent. So, you don't, if you were to go out into the, world and let's let's say you just started digging a hole and you said, I'm going to dig up some sodium. You're not going to dig up just raw sodium. It's not going to be there. What you're probably going to find is sodium chloride. Sodium likes to combine with chlorine. That makes table salt. So if you dig into the ground, you're going to find salt there, because by themselves, those elements don't like to stay by themselves, so they immediately form a compound. When they come into contact with one another, that makes them really stable. That gives them that net neutral charge, and then they don't do anything else. They're just kind of, it becomes salt, right? And we don't have to worry about it. So all of the elements, we have put them on a periodic table, and we call that the periodic table of elements. And so that lists every element with its abbreviation, which is either one letter or two, depending on the element. For example, the first element you see, element number 1, is hydrogen. It's going to be over on the far left of the table. And then element number 2 is helium. It's on the other side. So it just depends. A lot of them are named, a lot of them are very simple to name, like hydrogen or oxygen or nitrogen or carbon. They have, just one letter, and it's the first letter of that element. A lot of the other ones are named after, for example, like sodium. Sodium is not S. Sodium is Na. And it's either it's Greek, or it's some derivative of a language, or for some it's an older version of a name, or it's perhaps it may be named after the person who discovered it. And so it may be a different language. So not all of them are as simple as, just identifying the first letter, because obviously multiple elements have the same first letter. So we can't just have, C1, C2, C3, C4. So we have different things for that. But they all exist there on the periodic table of elements, and that periodic table identifies, the element's atomic mass, its atomic number. Okay, it identifies a lot of different things, and if you know how to read that table, then that can tell you a lot about the properties of the element and what it's more likely to combine with, and those types of things. So, outside of just our normal elements, we do have things called isotopes, and that is an atom of the same element that have a different number of neutrons in their nucleus. And so because of that, they have slightly different properties. So for example, you can have carbon 12, you can have carbon 14, you can have all these different versions of carbon because of the number of neutrons is different. And because of that, those isotopes have slightly different properties. And that's just that exists outside of just the normal, what you would ever find everyday carbon. But when elements do decide to combine, they can form compounds. And like I mentioned with sodium is usually going to be found in a compound of sodium chloride. Sometimes it's just two elements. Sometimes it may be more than that. But a compound is formed by anytime you have two or more elements which come together. Okay, so like this would be a compound. This is a compound of salt. It's a compound of sodium chloride. And there's a lot of people talk. Well, is it a compound? Is it a molecule? Molecules is the smallest unit of a compound. So, and it's still going to display the properties of that compound. What's the difference between the molecule and a compound is a molecule can be, for example, two oxygen atoms stuck together. That is a molecule of oxygen. But it would not be a compound because it's not two different elements, right? It's just two atoms of oxygen. And also, like, for example, water is H2O, okay? Because of the way hydrogen and oxygen bond with one another, water is a molecule, okay? But because it's two different elements, water is also a compound, okay? And it really boils down to how things come together, what type of bond they're using. So, for example, sodium chloride is a compound, but it is not a molecule because it doesn't have molecular bonds. Sodium chloride is held together by ionic bonds. So let's take a look at the different types of bonds. Compounds are either going to be put together one of two ways, either through an ionic bond or a covalent bond. In an ionic bond, the electrons are going to be transferred. So this electron from sodium is going to be moved to chlorine, and the chlorine is going to accept it. That changes the charges of all the atoms in the compound. and the opposite charges are attracted to each other. So sodium has a positive charge, chlorine has a negative charge, and then that charge is going to move from sodium to chlorine, and that creates an ionic bond. So that's why it's not a molecule. Covalent bonds, in contrast, they're going to form when two or more atoms share their electrons instead of having them be moved. So the electrons orbit around both nuclei, and you can have a double covalent bond, you can have a triple covalent bond, or you can have just a single covalent bond. It doesn't really matter. But those covalent bonds are also called molecular bonds, and so when they form that way, then you can call it a molecule. So it doesn't matter, molecule, compound, they're all going to be elements, and they're going to be combined one way or another, making up the substances that make life possible.